In sections 6.4 and 6.5 of Chapter 6, we'll start looking at masses and actually converting from numbers of molecules to masses back and forth. So in the previous section, we talked about the unit of a mole and how the mole relates to the mass of an element. So for elements, we know that the molar mass is going to be the mass of 1 mole of atoms of that element. So remember, a mole is 6.022 times 10 to the 23rd units, whatever you're looking at. It can be atoms, molecules, golf balls, oranges, whatever you've got. That's the number for a mole. Right? So molar mass is the number of grams mass in 1 mole of whatever you've got. For a compound, the molar mass is going to be the mass of 1 mole of molecules. Okay, so let me go ahead and just point this out to you right now. There we go. All right, so when we said elements, grams per 1 mole of element. For compounds, grams mass per 1 mole of either molecules or formula units. So remember, ionic compounds don't really contain individual molecules, so they're formula units. Now, that doesn't mean that the basic concept is any different from that of a molecule, but technically they are not the same thing. So if you do happen to call a formula unit for an ionic compound a molecule, we're not going to nitpick about that. Just as long as you're aware when you are dealing with bonding in them. When we get to bonding, it'll make a difference then. Right now, if you call them molecules, we won't quibble about that. All right, so we convert between the mass of a compound and the number of moles of a compound using the idea of molar mass. That's what relates mass to number of moles. Those are the numbers on the periodic table. Then we can calculate the number of molecules or formula units or atoms or whatever we've got once we're in number of moles. So what we need to remember in these types of calculations, anytime we're doing these conversions within masses and numbers for atoms, compounds, formula units, we have to keep in mind that the mole is in the middle. The mole is how you get from one side to the other. Okay, so you can't go from grams to numbers of atoms without going through moles. That's your translator. In order to convert between grams and moles of a compound, you of course have to have the molar mass. You have to have the relationship between mass and number of moles. So the molar mass is going to be numerically equivalent to formula mass of a compound in atomic mass units. So remember, we had those AMUs, those atomic mass units. That's going to be equivalent to formula mass, which is going to be grams per mole. So formula mass is just the sum of the atomic masses of all the atoms in a chemical formula. And this is what we looked at just at the very, very end of Chapter 5. We touched on it briefly. Now we're going to really start using that. Let's say, for example, we're asked to calculate the mass in grams for 1.75 moles of water. Right, so when we write it out, we know how much water we have in moles, 1.75 moles. And let's switch back to our pen down here. We're trying to find the mass, number of grams of water. All right, so this one's pretty straightforward. We're starting with moles. We want to get to grams. As long as we've got moles, remember moles are in the middle, so we can branch out. It's usually a one-step process from there. To get from moles to grams, all I need is the relationship between those two units. Okay, so grams, here's my relationship here. Moles, here's my relationship here. And I had to calculate the formula mass or molar mass for water. Now that's something they didn't show you where that came from. Where did 18.02 come from? All right, so just as a reminder, let's take a look at that. All right, so we needed the molar mass of water. Remember that we take the number of atoms, so the 2 comes from the subscript 2 right here with hydrogen. I have 2 atoms of hydrogen times the atomic mass of hydrogen, which comes from the periodic table. That's the 1.01 that you see here. And then the 1 right here comes from the 1 oxygen atom that I have. So I have 1 atom of oxygen times the atomic mass of oxygen. Again, I go to my periodic table and I find that it is 16.00. So when I multiply this out, I get 2.02 plus 16.00. That's where my total comes from, 18.02. All right, so there's my relationship between grams and moles of H2O. So now what this is, the relationship to 1 mole, but I don't have 1 mole. I have 1.75 moles. So I need to ratio that. I have a little more than a mole. So 1.75 moles of water times the 18 grams for every 1 mole of water. Moles cancel out, and that tells me that in my 1.75 moles of water, I have 31.5 grams of water. Okay, so let's look at an example where we're not starting with moles. We don't start with moles in the middle. Let's say that we're asked about nitrogen dioxide, NO2, right here. And we're asked to figure out the mass. So what is the mass in grams of 4.78 times 10 to the 24th molecules of this gas? Right, now in this case for our solution map, notice there's no moles in here. We're given we're given molecules, so we're given units, and we're trying to find grams. I cannot just directly go from one to the other, okay? That doesn't work because molecules are based on numbers and grams are based on size, essentially. That's like saying, if I have 80 golf balls, how many grams of golf balls do I have? Well, I need to know how much 1 golf ball weighs in order to figure out if I have, 80 or however many golf balls I have. I need to know the mass of 1 so I can multiply up. That's what moles is. So now we've got moles in the middle. We're going to start with the number of molecules and we're going to go to moles. Okay, so here's the relationship. There's moles. I'm getting to there. Here's molecules. Okay, so I'm trying to go from molecules to moles. Remember that relationship. 1 mole of anything, does not matter what it is 6.022 times 10 to the 23rd. That is a constant relationship for moles to particles. Okay, that will give me number of moles. Now I've got to get from moles to grams. Now I can go from these counting units to mass because of that relationship, those kind of atomic mass units on the periodic table. So here are my grams. Okay, that's what I'm trying to get to, and here's the moles where I'm starting from. Now if you look at this, you'll kind of notice a pattern. When I'm going from one thing to the other, whatever I'm starting with, it's in the denominator. I'm trying to get rid of it. Whatever I'm trying to get to is in the numerator. That's the unit I'm trying to get to. So again, I'm calling you back to that dimensional analysis. If you don't need dimensional analysis to see what's going on, that's fine. You can work the problems, but it's a really good idea to write it down that way and show it just to show the flow of those units. I still use dimensional analysis all the time. I've been in chemistry for longer than I care to admit here on tape, and kind of dated myself saying tape even, but at any rate, you do want to show that dimensional analysis if you have any trouble at all understanding where these units are coming from. All right, so here's my solution map. Now let's look at it worked out. Okay, again, you know the relationship between moles and molecules, but the 46.01, where did that number come from? We have to find that number before we can plug everything into our map. Okay. Now they showed you the 46.01, but before you can make your solution map, you have to do the relationship right here that they showed. They calculated this and showed it to you on the last slide. They did that first, so you would need to do this first. All right, so here's relationship number 1. 6.022 times 10 to the 23rd equal to 1 mole. This is relationship number 2 right here, molar mass, grams per mole. Okay, and remember that's the number of grams in 1 mole. So there's one atom of nitrogen right here, nitrogen, there's one of those. The atomic mass of nitrogen from the periodic table is 14.01. Okay, there's a 2 here that comes from the subscript 2 with the oxygen. And then the atomic mass of oxygen, again, you go to your periodic table, you should have it out by now and be looking at it, is 16.00. Now oxygen is one you'll probably end up having memorized after a while because oxygen appears over and over and over again. The ones you use more often, you'll start to recognize those atomic masses, but in the meantime, keep that periodic table open, keep it in front of you. All right, 14.01 plus 2 times 16 is 32, so 32 plus 14, 46.01 that you've got here. All right, so now we can start with what we're given. 4.78 times 10 to the 24th molecules times the 1 mole per 6.022 times 10 to the 23rd. Got our Avogadro's number. That's the number of molecules. Those cancel out. Okay, so that's leaving us with units of moles, but we don't want moles. We want mass in grams. So now we use our relationship of 46.01 grams of nitrogen dioxide for every 1 mole of nitrogen dioxide. Moles of nitrogen dioxide cancel out. That leaves us with 365 grams of nitrogen dioxide in this number of molecules. Now, if we think about it, does that make sense? That's a reasonable number. We know that, in 1 mole, we've got 10 to the 23rd molecules. This is 10 to the 24th, so we should be looking at a little more than a mole there. Okay, we've definitely got more than a mole. And so more than a mole, if 1 mole is 46, more moles should have a higher mass. If this number had been smaller than Avogadro's number, I would expect this to be a mass less than 1. I would expect it to be a very small mass. So kind of use your reasoning to double check yourself and make sure it looks right. All right, so now that we know how to convert between particles, such as atoms or molecules or formula units, and number of moles, and mass in grams, now how can we use that when we start talking about our chemical language? To this point, we're looking at relationships for one particular compound, but we know that we don't have just one compound. We have thousands of compounds, and those compounds don't necessarily stay those compounds forever. They carry out chemical reactions. They react together and make new compounds. So it may not be enough to be able to figure out the mass of this compound. This nitrogen dioxide, for example, reacts with water and forms nitric acid. We talked about that earlier. So when that happens, if I know how much nitrogen dioxide I started with, how can I predict, how can I calculate how much water it will react with and how much nitric acid will form? That's what we're going to start doing. We're going to use predictive power. Okay, and this is sort of like the pizza example that we looked at in class, where if I take all the various ingredients of a pizza and put them together, I end up with this new entity called a pizza. Okay, so how do I know how many pizzas I have? Well, it depends on how many ingredients I started with. And we want to look at that concept next. Another analogy that you could use, that your book uses, is that of a 3-leaf clover. Okay, so if I have 3-leaf clovers, how many leaves do I have on 14 total clovers? You don't really probably need to think about it very much to figure that out. You know what to do with that. You've got 14 clovers, there's 3 leaves on each one. You multiply 14 times 3. Okay, but how does that break down? Again, it makes perfect sense with clovers and leaves. It may not make as much sense when you're talking about nitrogen dioxide versus nitrogen atoms or something like that. So again, let's take something familiar, leaves on a clover, and break it down into our process so that we can then use that process as a model for looking at things that aren't familiar. All right, so here's our ratio. We've got 3 leaves for every 1 clover. So clovers to leaves is 3 to 1. 14 clovers times 3 leaves on every 1 clover. Clovers cancel out, and it leaves me with leaves. I find that I have 42 leaves in those 14 clovers. Makes sense, right? All right, so let's do the same thing for a molecule. Let's look at carbon dioxide. It's 1 carbon to 2 oxygens. Okay, so 2 oxygen atoms for every 1 carbon dioxide molecule. Okay, so I can write that relationship in different ways. I can say there's a ratio of 2 oxygen atoms to 1 carbon dioxide molecule. Excuse me. I can say that I have 2 dozen oxygen atoms for every 1 dozen carbon dioxide molecules. Okay, so dozen to dozen. Or I can say there are 2 moles of oxygen for every 1 mole of carbon dioxide. Okay, this is a very powerful thing for us, knowing what we call the molar ratio and using it as a conversion factor. So now, if I know how many moles of carbon dioxide I have, I know how many moles of oxygen I have. I have twice as many. I also know how many moles of carbon I have. It's the same as the number of moles of carbon dioxide. Because remember, mole doesn't have anything to do, well, I won't say it doesn't have anything to do, but moles are counting numbers. It's telling you how many of something. Okay, so it may seem a little counterintuitive if I have 1 mole of CO2, how can I have 1 mole of carbon? It's just the number of them. You don't have to cut it in half or anything. I didn't cut the atoms in half. There's 1 there for every 1 of the whole. Looking at some more analogies for that, spiders have a ratio of 8 legs to 1 spider. Okay, so this spider has, 8 to 1 for that. Now, so this would be like, 2 oxygens to 1 carbon dioxide, 8 legs to 1 spider. If I was talking about the body of the spider, I would have 1 body for every 1 spider. That's like 1 carbon for every 1 carbon dioxide. Or if I look at a chair, 4 legs for every 1 chair. I look at water molecules, 2 hydrogens to every 1 water molecule. Okay, so it's like the legs on a chair, legs on a spider. If you think of this oxygen atom as being like the body, okay, it's got 2 legs. Think of it that way, maybe. So, how do I use it? How do I go to those calculations? Right, keep in mind when you're looking at these calculations, it's more than just numbers. Try to keep that concept in mind, that it's the number of units in the whole, the number of legs attached to the body. So if I want to know the number of moles of oxygen in 1.7 moles of calcium carbonate, if I look at this, here's my spider. How many legs does he have? If legs are oxygen, he's got 3 legs. So I use my ratio. I start with my 1.7 moles of calcium carbonate. I'm looking for number of moles of oxygens. So I have 1.7 spiders. How many legs do I have? Right, ratio is 3 to 1. So, got my relationship here. I start with my 1.7 moles of calcium carbonate. Now, this number is just coming from the subscript. 3 moles of oxygen. Okay, so the 3 is related to this guy right here. That's where it came from. 3 moles of just the oxygen in every 1 mole of calcium carbonate. 3 legs on 1 spider. And so kind of a weird spider, maybe not a spider, so we've got a tripod here. So 3 legs on a tripod. I have 1.7 tripods, so when I multiply it out, I find that I have 5.1 legs on my tripods, 5.1 moles of oxygen in this case. Alright, so that's if we have number of moles, and remember, moles are in the middle, so if I'm starting with moles, it's easy to go to molecules, grams, or to convert from one type of mole to another. Now, in all of the cases before the one you're looking at now, we were looking at what we call the same chemical species, the same compound. So when I talk about a chemical species, if I'm talking about sodium chloride is the species, or here, calcium carbonate. Calcium carbonate is a chemical species. Oxygen is a different chemical species. So what this is telling us is if we want to switch from one species to another, see if I can write with this here, ECIES, I hope you can read that. Okay, I have two different species here. Okay, if I am trying to convert from one species to another, I have to do it in terms of moles, mole to mole. All right, so now I can go from grams of calcium carbonate to moles of calcium carbonate. I can go from moles of oxygen to grams of oxygen. I cannot, for instance, let's say I had grams of calcium carbonate and I wanted to know moles of oxygen. Okay, I cannot do that directly. Does not work. It has to go into grams of calcium carbonate to moles. Grams to moles has to be the same species. Now I can change from one species to another in terms of moles, and then I can move on from the moles if I need to. As always, we will look at an example of that. All right, so I want to know the mass of sodium. So mass is telling me I want to find grams, okay, of sodium, Na. That's what I'm trying to find, grams of Na. I am starting with 15 grams of NaCl. Now, that may sound simple, grams of one to grams of the other. I can't go directly there. There is no one single conversion factor to get me from grams of this to grams of this. What I have to do is start with grams of sodium chloride and convert to moles of sodium chloride. Notice the species does not change. I can change the unit or I can change the species each step. I cannot change them both at once. So in this case, I'm going to change from grams to moles of the same thing. Once I have moles of sodium chloride, now I'm going to keep moles the same. Now I'm going to change the species. Okay, so here I changed units. Now I'm going to keep the units, mole and mole, and then change the species. Okay, so changing to sodium. Once I've done that, now I am going to keep the species again, and I am going to change the unit. Okay, so let me take that, see if it, yeah, it won't let me back up on that. So moles to grams of the same thing, of sodium. So I need the relationships for each one of these steps. So from grams to moles, if I want to change grams to moles, that's telling me grams and moles are related by molar mass. I need the molar mass of sodium chloride. So I look up sodium on the periodic table. Sodium is 22.99 grams in 1 mole. Chlorine is 35.45 grams in every 1 mole. And I have one of each of them, so 1 times 22.99 plus 1 times 35.45 equals 58.44. So there's that relationship. All right, now this relationship, the moles, it's moles on top and bottom, but I need to know how many sodiums in a sodium chloride. Well, because it's a subscript of 1, there's just 1 mole of sodium for every 1 mole of sodium chloride. And then in the last one, I need molar mass again. Well, this is just sodium from the periodic table, so I can look up that number. There's the 22.99 grams in every 1 mole. Now I can plug these all in. I start with my 15 grams that they gave me. Okay, I plug this one in, lets grams cancel out, and it leaves me with moles of sodium chloride. Then I plug this one in, 1 mole of sodium to 1 mole of sodium chloride. This may seem like a very silly step to you because I'm multiplying by 1 over 1. I'm multiplying by 1. I'm not really changing anything. If I'm looking just at the numbers, yeah, I'm not changing anything. But the thing is, I'm changing much more than just numbers. I am changing chemical species in terms of moles. So be sure that you do not leave this step out. Okay, this is a molar relationship. This is going to come into what we call stoichiometry when we start looking at equations. This is a very, very critical concept to understand. The ratio of atoms in a molecule, or the ratio of molecules from one side of an equation to another. Do not leave it out. Even if it's 1 to 1, plug it in there. You won't regret it later. Okay, so 1 to 1 there. All right, now I come back and plug in. I'm dealing with moles of sodium now. I have magically changed from sodium chloride to sodium. I have a new species, and I want to know the mass of that species, 22.99 for every 1 mole. So I end up, when I do the math, 15 divided by 58.44 times 22.99. The rest are all ones. I find that I have 5.9 grams of sodium in 15 grams of sodium chloride. All right, so getting molar relationships from a chemical formula is so critical. This is what I was just saying. So for example, if I have a mole of carbon tetrachloride, so the black circle in the middle is the carbon, and then it's got 4 legs, it's got 4 chlorine atoms attached to it. Okay, ratio for 1 mole of carbon tetrachloride, there are 4 moles of chlorine. Okay, how many moles of carbon would you have in there? You'd have 1. So we can get those relationships. That allows us to convert between the moles of the compound and the moles of any constituent element, and back the other way, which gives us power to look at, if I broke it apart, then how much would I need to react with something else to completely react that? All right, so that's molar relationships in a nutshell. We're going to get much more involved with those, but just really quick, in your book, there's a little plug for a couple of environmental items that I just want to call your attention to, because they come into play with this idea of molar ratios, and just very interesting to know. So when we're looking at those relationships, like that carbon tetrachloride that I showed in the previous slide, sometimes those compounds, well, not sometimes, those compounds are known as chlorofluorocarbons. These are compounds that contain, they're usually carbon-based compounds that contain chlorine and or fluorine, and that's abbreviated as CFCs. And you may have heard of CFCs in the news, you might have read about it in articles. The reason you've heard about it is because CFCs destroy a compound called ozone, which is just 3 oxygen atoms that are bonded together. Now, ozone is a little bit of a Jekyll and Hyde compound, because if you've ever heard people talk about ozone levels in a city, they're talking about pollution levels. They're talking about things that are bad. Ozone at our level, if we're breathing it in, is very bad for us. It's also very bad for reacting with compounds that then creates new things that are very bad for us. So we don't like ozone down here where we are on the surface of the earth. But, okay, so Jekyll and Hyde here, we like ozone to be in the upper atmosphere for the very same reason we don't like it on the surface of the earth. It's very reactive. Ozone reacts with ultraviolet light coming in, and very high energy ultraviolet light. Now we know ultraviolet light can have harmful effect on us as biological beings. It causes skin cancer, it causes mutations within our cells. It's not good for us. So we like to have UV light filtered out. Ozone is what is responsible for filtering out those ultraviolet rays. Okay? Now the problem is CFCs are, generally speaking, chemically inert molecules. So here on the surface of the earth, where we are, they don't tend to react with a lot of things, and they're used as refrigerants, industrial solvents. So if you've ever heard of Freon that you use in refrigerant, that is a CFC. Okay, and it's not the only one. There's lots of them, and there's other refrigerants that we use that are on that same basis. All right, what happens is these CFCs, which are inert down here where we are, get into the upper atmosphere, and then that ultraviolet light hits the CFCs instead of the ozone. Okay, they do react with the energy from sunlight, and they break apart. And when they do, Okay, depending on the ratio, how many chlorines you have in there, it releases chlorine atoms. They're no longer CFCs. They're chlorine atoms, fluorine atoms, carbon atoms floating around. The chlorine atoms react with ozone, okay, and basically they destroy the ozone because they break it down from O3 to O2. Now, that doesn't sound too bad. O2 is what we have here on the surface of the Earth that we breathe. We can't do without it. Okay, but again, kind of a reverse here. O2, good for us down here on the surface of the Earth, doesn't really do much for us. It's not harmful in the upper atmosphere, but it really doesn't help us because O2 is not capable of absorbing the energy from those ultraviolet rays. It takes O3, it takes the absorption power of that extra bond in order to stop that ultraviolet light. So O2 just lets the ultraviolet light through, okay, and it causes harm to living things like inducing skin cancer in humans and other animals as well. It creates, a difference in reactions in plants. Leaves can be harmed by that extra ultraviolet light, so they're getting mutated reactions. So not a good thing. Okay, we've recognized that as not being a good thing worldwide, and most of our developed nations have banned production of CFCs. That's been back as far as 1996. Now that doesn't mean that there are no CFCs left. There's still plenty of it out there in old refrigerators, old air conditioning units that people don't dispose of properly. They wait until it's dark and toss them out on the side of the road. The refrigerant container will break open and release it into the atmosphere. And you think, oh well, one's no big deal, but if everybody's doing that, it creates a lot of problems. Okay. All right, so just another little graphic here. Upper atmospheric ozone, very important to us. It acts as a shield to protect us from this UV light coming in. UV light, not good, we don't want it. We like to have our ozone block that out. Okay, so when ozone is gone, we have a problem. That stuff comes right in. All right, so we know that CFCs tend to get concentrated in the upper atmosphere in different areas over the Earth, and that's just because of the movement of air and wind and different things, and not so much air in the upper atmosphere, but the movement of particles and the movement of our atmosphere. And so, most of the CFCs and the other things, and the CFCs aren't the only ones. There's a lot of things that will destroy ozone, but CFCs are the biggest one. Got concentrated over the South Pole, over the Antarctic. So there's an Antarctic ozone hole that we first started noticing in the late 70s, early 80s. Okay, and what they're doing here is showing a mapping of data. They started collecting data about how big the ozone hole area. When we say a hole, it's more like a severe thinning of the ozone layer. It's not a hole per se, but it's just a very, very thin area of ozone. They plotted it from 1980 all the way up to 2012, and you can see here how quickly that climb was up until 1996. Here's where they started banning the production. All right, now you'll notice it's not like it just immediately dropped off. What it's done is sort of leveled out. It's climbing down just a little. It's climbing down very slowly, but it had to kind of level out because those CFCs, even though we don't produce them anymore, they're still out there. That ozone that's been destroyed, it it can be regenerated through different reactions, but it takes a long, long time to regenerate that ozone. So it's going to be a long process. It means we've got to really kind of take care of it. It's sort of like if somebody has a very bad burn on their skin and they have to have a skin graft. Well, that new skin from the skin graft is going to be very delicate for a long time, and you really have to be careful and take good care of it. And that's kind of where that ozone is right now. It's like a skin graft that we need to take care of. All right, so there's a little plug for the environment there. That wraps up section 6.4 and 5, and then we'll move along to the next two sections dealing with chemical composition.